Google Willow. When quantum machines become unstoppable. Imagine a calculation so enormous, so mind-bogglingly complex, that today's fastest supercomputer would take, get this, not thousands, not millions, but 10 septillion years to even try. That's a number so big, it makes the age of the universe look like a blink. Now picture a new kind of machine, a quantum processor, that cracks that exact same problem in under 5 minutes. Sounds like sci-fi, right? But this is the reality of Google's Willow chip, revealed in late 2024. And it's making us think we might be on the cusp of an era where quantum machines genuinely start to become unstoppable. Section 1. The Grand Challenge and the Quantum Dilemma. For decades, we've been riding the wave of classical computing. Transistors got smaller, speeds got faster, and our world changed. These computers, built on bits that are either a 0 or a 1, have been incredible. But some problems, deep scientific mysteries, super complex optimization puzzles, the next frontiers of AI, are just too tough for even the beefiest classical supercomputers. Their step-by-step approach just hits a wall when things get exponentially complicated. This is where the weird and wonderful world of quantum computing steps in. Instead of classical bits, quantum computers use qubits. Thanks to bizarre quantum mechanics principles like superposition and entanglement, a qubit can be a 0, a 1, or a mix of both at the same time. This unique trick lets quantum computers explore a massive number of possibilities all at once, offering a shot at computational power that classical machines can only dream of for certain jobs. The potential is huge, designing new life-saving drugs, molecule by molecule, creating materials with properties we can't even imagine today, shaking up financial modeling, and maybe even helping us unlock deeper secrets of the universe. But this amazing quantum promise has always had a massive catch. Qubits are incredibly fragile. Think of them as being super sensitive. The tiniest disturbance from the environment, a bit of heat, a stray electromagnetic field, can make them lose their delicate quantum state. That's called decoherence, and it causes errors in calculations. Historically, the more qubits scientists tried to link up to build a more powerful quantum computer, the more errors would sneak in, and the more unstable the whole thing became. It felt like a fundamental roadblock. Bigger quantum computers meant more noise and more mistakes. For quantum machines to ever be truly unstoppable, this error problem needed a revolutionary fix. Section 2. Enter Willow, the breakthrough. And that revolutionary fix might just be here. In December 2024, Google Quantum AI pulled the curtain back on the Willow processor, a chip that many are calling a huge milestone in the journey towards practical quantum computing. Willow isn't just a small step up. It's a leap forward that tackles the quantum error problem head-on. At its heart, Willow is a 105-qubit superconducting quantum processor. That's a big jump in qubit numbers, roughly double its predecessor Sycamore, which made waves back in 2019. But Willow's real magic isn't just about how many qubits it has, but how good they are, and crucially, the groundbreaking way they work together to squash and correct errors. The Willow chip was painstakingly designed and built at Google's special cutting-edge quantum hardware lab in Santa Barbara, California. This place is one of only a few in the world built from scratch, just for making these advanced quantum devices. This kind of precise engineering is vital. It makes sure all the chip's complex parts, from individual qubits and the 2-qubit gates that link them, to how qubits are reset and read out, not only work well on their own, but also work together perfectly. This all-in-one approach to design, building, and tuning is key to Willow's improved performance. The chip boasts these 105 superconducting qubits with an average connectivity of 3.47, which allows for the complex interactions needed for advanced quantum calculations. But the feature that's really got scientists talking and signals a new phase in quantum development is Willow's unprecedented error correction. This is where the path to unstoppable quantum machines really picks up speed. Section 3. Willow, a technical marvel. For years, the dream of large-scale quantum computing was haunted by a tricky paradox. When researchers tried to build bigger quantum computers by adding more qubits, the systems often got noisier and more error-prone, not better. Willow smashes this idea with something that's been a theoretical goal since 1995. It shows it can operate below threshold. What does below threshold actually mean? It's a major turning point. It means that as you cleverly add and arrange more qubits in the Willow system for error correction, the overall error rate of your logical calculation doesn't just hold steady, it actually goes down exponentially. Google's researchers proved this by creating arrays of physical qubits in bigger and bigger grids. Each time they expanded the grid, the error rates dropped significantly. This is the holy grail of quantum error correction, getting a system that naturally becomes more reliable as it gets bigger. As Hartmut Neven, founder of Google Quantum AI, put it, this is an unfakeable sign that quantum error correction is genuinely making the system better. This isn't just theory. Willow actively does real-time error correction on a superconducting quantum system. It uses a smart technique called the surface code, where the information of a single, more robust logical qubit is spread across multiple physical qubits. If errors pop up in some of these physical qubits, which they inevitably do, the surface code lets the system find and fix these errors, keeping the overall quantum computation on track. Willow's integrated real-time decoder is impressively fast, with a cycle time of just 1.1 microseconds, allowing it to spot and correct errors super quickly. This speed is absolutely essential, because errors need to be caught and fixed faster than they can pile up and mess up the whole calculation. On top of these error correction smarts, Willow also shows big improvements in how well its physical qubits perform. The T1 coherence time, a key measure of how long a qubit can hold its quantum state, has jumped up 5 times compared to Google's older Sycamore chip. Willow's T1 times are now getting close to 100 microseconds. This much longer coherence time means more complex and longer quantum algorithms can run before the delicate quantum states fade away. Plus, the fidelity of both single-qubit and two-qubit gates, which is basically how accurately quantum operations are performed, has also improved by about a factor of 2. And then there's the raw computational power. Willow's abilities were put on stunning display with a benchmark test called random circuit sampling, RCS. This kind of task is designed to be incredibly hard for classical computers, even supercomputers. In these tests, Willow nailed a complex RCS computation in under 5 minutes. To give you some context, it's estimated that even the world's most powerful supercomputers would need an unbelievable 10 septillion years, that's a 1 followed by 25 zeros, to do the same job. This isn't just about being faster than classical computers. It's about showing a quantum advantage on a scale that blows previous achievements out of the water. Section 4. The dawn of unstoppable machines? So what does all this techie stuff, this ability to do weird random circuit sampling incredibly fast and to fix its own mistakes better and better, really mean for the future? Why is a chip like Willow such a big deal? It means we're taking real solid steps towards the ultimate goal of fault-tolerant quantum computing. Fault tolerance is the point where quantum computers are big enough, and their errors are controlled so well that they can reliably solve important real-world problems that are currently way beyond our reach. Willow's demonstration that error rates can actually go down as the system gets bigger is a fundamental, game-changing proof that this vision is possible. It strongly suggests that building even larger, more powerful, and at the same time, more reliable quantum computers is a doable engineering challenge, not an impossible scientific dream. The implications of this progress are huge and could touch almost every part of science, technology, and industry. Think about drug discovery and materials science, for instance. Quantum computers, building on what Willow has shown, could simulate how molecules and chemicals interact with an accuracy and complexity that's just impossible today. This could let scientists design new life-saving medicines personalized for individuals, create new catalysts for cleaner energy, develop much better batteries for electric cars and power grids, or even engineer entirely new materials with amazing properties like superconductors that work at room temperature. In the fast-growing world of artificial intelligence, quantum machine learning algorithms, when run on future fault-tolerant quantum systems, could revolutionize things like pattern recognition, complex optimization, and analyzing massive data sets, potentially leading to AI breakthroughs we can barely even imagine right now. Really tricky optimization problems, like making global supply chains run smoother, creating more accurate financial models for risk, or efficiently routing citywide transport in real time, could find much better solutions. Even basic scientific research stands to gain a lot, with the potential to accurately simulate complex quantum systems in physics and chemistry. This could lead to a much deeper understanding of the universe at its most fundamental level. And while the incredible power of quantum computers does raise fair concerns about breaking current encryption, the field of post-quantum cryptography is actively developing new, quantum-resistant encryption methods to keep our digital information safe in the coming quantum age. The word unstoppable might sound like a bit much at first. However, Willow's achievement strongly suggests that the progress in quantum computing is now building a powerful, maybe even unstoppable momentum. By successfully showing scalable quantum error correction, Google has given us solid, real evidence that one of the biggest and most stubborn hurdles to large-scale quantum computation is starting to give way to human cleverness. Section 5. The road ahead and lingering questions. While Google's Willow chip is a massive achievement and a huge leap forward, let's keep our feet on the ground. This is a critical milestone on a long road, not the final stop. We're still in the early days of the quantum computing era. As Google's own quantum team admits, the next big challenge is to go beyond benchmarks like random circuit sampling and show a useful, beyond classical computation. That means tackling a practical, commercially relevant problem that classical computers can't realistically solve, thereby showing off real-world uses. Building a truly fault-tolerant logical qubit, one that's corrected well enough from errors to be used in the most complex quantum algorithms, will likely mean using hundreds, or maybe even more than 1,000, physical qubits to encode it. So, while Willow's 105 physical qubits and its proven error correction with arrays like a 7x7 setup are impressive, the journey to quantum machines with many thousands or even millions of high-quality, interconnected logical qubits is still very much ongoing. The path to fully fault-tolerant quantum computing will need non-stop innovation on many fronts, in designing and making even better physical qubits, in developing smarter control systems, in fine-tuning quantum error correction codes, and in creating new quantum algorithms. Plus, this is a global effort. Other big tech companies and top research institutions, including IBM, Intel, Microsoft, IonQ, and Xanadu, are also making big strides, often trying out different quantum hardware ideas and adding to the collective progress of the field. This lively and competitive scene is definitely a good thing and will help speed up progress overall. Some industry watchers, while recognizing how amazing breakthroughs like Willow are, suggest more cautious timelines for widespread practical impact. Predictions vary, but some think it could still be a decade or possibly longer before we see super advanced quantum computers tackling a wide range of complex commercial jobs. Nevertheless, achievements like Willow have definitely energized the field, and for many have shortened the imagined timeline to useful quantum computation by proving that one of the scariest scientific and engineering challenges, scalable error correction, can indeed be overcome. Google's Willow chip has undeniably kicked off a new and exciting chapter in the ongoing quantum revolution. It's a powerful testament to years of dedicated scientific research and brilliant engineering, and it shines a bright light for future innovation in computing. We're keen to hear what you think about this incredible step forward. What potential uses of quantum computing get you most excited? Or perhaps, what parts make you stop and think? Share your thoughts in the comments below. And if you want to stay in the loop on the mind-bending, fast-moving world of quantum breakthroughs and how they'll shape our future, make sure to subscribe to the channel and hit that notification bell. Conclusion. Google's Willow is much more than just an impressively powerful new quantum chip. It marks a fundamental shift, a key moment in our rapidly growing ability to control and effectively use the counterintuitive yet powerful laws of the quantum world. By showing for the first time in a really compelling way that quantum systems can indeed become more reliable as they get bigger. Willow has laid crucial groundwork for an entirely new era of computation, an era that promises to unlock abilities far beyond anything classical machines could ever dream of achieving. The journey towards truly unstoppable quantum machines, those advanced, fault-tolerant systems capable of solving some of humanity's most complex, urgent, and currently unsolvable problems, is certainly still a long and challenging one. There are many more milestones to hit. But with breakthroughs as significant as Willow, that once distant future feels a lot closer and much more real than ever before. We are, essentially, watching the dawn of an age where the computationally impossible starts to bend to human ingenuity, powered by the very fabric of reality that quantum mechanics describes. The era of truly unstoppable quantum computation might not be fully here just yet, but Willow has definitely and brightly lit the way forward.